Okay, now we are going to analyze the entropy of systems. All right, so I want you to remember before we start to do this is example 14.5 on page 436. When I talked in the last clip about the change in entropy of the universe, all right, delta S, it's the S of the delta S of the system, which would be, this would be the system, plus the delta S of the surroundings, which would be the air and everything around this reaction. That has to be greater than or equal to 0. Now, for these two reactions in example 14.5, we are just taking into account the delta S of the system. And because of that, delta S can be negative. It can be lower than 0. The overall system and surroundings cannot be less than 0, but the system itself can be less than 0, because that way the surroundings would be increasing in entropy to offset that. All right, so you got to keep that in mind when we're looking at these examples and being able to analyze whether something is going to increase the entropy or increase the chaos or disorganization, or whether it's going to decrease it. All right, so before we get started on these, there is a pink box on page 436, and it gives us two ways to know whether entropy is going to increase or decrease. All right, so number one, it says the solid phase is the lowest entropy phase. We already talked about that because there's more organization. The molecules are closer together. They can't move very much. Well, the gas phase is the highest entropy phase. We know that. They're all over the place. There's a lot of chaos there. All right, number two, though, the larger the number of molecules, the higher the entropy. That makes sense, too. If you have more Legos, you're going to make a bigger mess when you throw them on the floor. Okay? If you throw a bucket of Legos on the floor versus you throw a handful, there's going to be entropy in both of them. There's going to be chaos in both of them, but if you have more Legos, there's more entropy, more chaos. All right? So the number of molecules, the higher the number, the higher the entropy. Both of those have to be taken into account when you're deciding whether a system is going to have an increase in entropy or a decrease in entropy. So if we look at the first one on example 14.5 on page 436, we have this equation that we used before for the delta H. We have the hydrogen peroxide, okay, in the aqueous phase, decomposes to form water in the liquid phase and oxygen in the gas phase. So the question is, what is the sign of delta S for the following reaction? Remember, positive delta S means there's more entropy, there's more chaos, okay? And we are looking, again, at the products minus the reactants. So we're looking at the product side, we're looking at the reactant side. Now, we have aqueous phase. All right, that's going to be somewhat midway in entropy as far as phases go, right? And it is going to decompose to make a liquid phase, which is, pretty similar to the aqueous, but it's also forming a gas. And so because it's forming a gas, the entropy is going to increase. As this system moves forward, as this decomposes, it's making a gas, it's forming a gas, and so the entropy is actually increasing. The phase is more important in determining the entropy of a system than the number of molecules. So even though they both have to be taken into account, the phase is going to be the biggest thing. So before we even look at the number of molecules, we know that the entropy is going to increase because a gas was formed when there was no gas on the reactant side. Now, if you take into account the number of molecules as well, we have two molecules here. This whole thing is one molecule. So you're not looking at all these numbers, you're only looking at these numbers. So we have two molecules over here, right? And then on the product side, we have two molecules plus another is 3. So we're going from 2 molecules here to 3. So not only are we going to a gas phase that increases entropy, we are actually also going from 2 molecules to 3. So in both ways, the entropy of just this system is increasing. All right? So if you look at the second one, also, it starts on page 436, and then there's another one on page 437. But so on page 436, the second one, we have 2 moles of carbon monoxide in the gas phase. So we have a lot of entropy going on, plus oxygen in the gas phase forms 2 molecules of carbon dioxide also in the gas phase. Well, if you're looking at the phases, then we have the same. They're all in gas, so there's a lot of entropy on both sides. You can't determine by the phase on this one whether it's going to be a positive or negative delta S. And so you need to look at the number of molecules. So we have 2 molecules here plus 1 molecule here. We have 3 molecules on the reactant side, and we only have 2 molecules on the product side. All right, so again, with it being products minus reactants, we have 3 over here, we have 2 over here. This delta S is going to be negative. And again, for the overall universe, you can't have a negative delta S. But for a system not taking into account the surroundings, the delta S for this system is going to be negative. It's going to be less than 0. All right, and so I want you to try to do the last one of this example. It's at the top of page 437. I want you to do that one on your own. I also want you to do the comprehension checks on page 437, numbers 9 and 10, just to get some more practice recognizing the entropy and what goes into it. So again, we're looking at the phases, and the gas phase is going to be higher entropy, more chaos than the solid phase. The gas is more chaos than the solid. Liquid is more chaos than solid, but less than gas, all right? And the number of molecules when the phase is all the same is going to increase the entropy. More molecules, more entropy, more chaos. Okay, so if you look at the table at the bottom of page 437, the delta S is also a state function, which means that we can take into account each individual thing, or we can look at entropies of molecules. And so we're going to take the shortcut again. We're going to take the straight road instead of going the windy. And so the table at the bottom of page 437 gives us absolute entropies. And you look at this, the absolute entropy is S0 or degree. And what that means is, again, it's going to be at 25 degrees Celsius or 298.15 K. And if you look at the units on this table, this is why K matters. You're going to be given temperatures in Celsius because we don't talk about temperatures in Kelvin. However, if you look at the units for this, it is joules per mole times Kelvin. All right? So that is a really important unit to remember when you're talking about entropy. It is in joules per mole times Kelvin. Okay, so when you're given 25 degrees Celsius, which typically you're going to, so almost, well, because this table is at 25 degrees, every time your Kelvin is going to be 298.15. But you have to have it in Kelvin. You cannot leave it in Celsius. All right, so if you do some calculations using that table, if you look at the page 438, the pink box, you calculate the delta S the same way that you calculate delta H, okay? And so I'm not going to go over this again. You can look at that pink box and be able to do these calculations on your own. So I want you to do that. Do example 14.6, do the comprehension check, practice those. And I just want to show you one more thing before I close out for the day, for the week, and then we'll pick back up later on. I don't know if it'll be later this week or next week. I want to try to keep onto a schedule that we would be doing if we were in class. But one thing I wanted to point out to you is the difference between the units of delta H and delta S. All right. So our units for the delta S, okay, delta S are the joules per mole times Kelvin. All right, delta H, if you'll remember, are kilojoules per mole. Okay, so you see we have joules there, we have kilojoules there. That's going to matter when we go to Gibbs free energy. So you have to remember these. Okay, I don't know if on the test, I actually believe that the units are given to you. Let me double check. If the units are given to you, then you just need to remember in your calculations that has to be taken into account, all right? When you are doing the Gibbs free energy, which again, we'll do next week. You can read ahead and try it on your own. It's not going to be hard to do, so I would love for you to try it on your own. But the when you are given, yes, you are given the units. So you don't have to remember what those units are, but I wanted to point this out to you so you pay attention to the difference in this. So you're going to have to convert the, let's see, let me see what units they go with joules. So you're going to need to convert this kilojoules to joules, all right? When you do these calculations. You could also convert the joules to kilojoules. It doesn't matter. They just have to be the same in order to do these calculations, because you're going to be off by powers of 10 if you leave the numbers how they are when one is in joules and one is in kilojoules. All right. So again, try the example 14.6. I want you to remember that pink box on page 438. And so now you're able to calculate the delta H, which is the enthalpy change. You're able to calculate the delta S, which is the entropy change. And we will put that all together in next week's lesson, or like I said, you can do it earlier on, to be able to calculate the Gibbs free energy, which tells us whether a reaction is going to happen spontaneously or whether it's going to need help to get started. All right. So I'm going to close out this video, and this does it for the week. Again, work on this stuff on your own. If there is anything that you need help on that you don't understand, you can call me, you can text me, you can email me anytime, and I will help you out. All right? Thank you guys, and have a great week.